Hello and welcome again to A Minute with a Molecule. In this episode, we have a slightly different twist. Here, a student came to me and presented what he felt was the Lewis structure of bromine trifluoride, stating that each of these green structures here represented fluorines, and that this purple structure here in the middle represented bromine. The student stated that bromine has 7 valence electrons and fluorine has 7 valence electrons, forming covalent bonds like this. That's correct. Fluorine getting its octet, that's correct. Bromine with access to a d orbital system, being able to break the octet rule. And all of that is totally correct. The student even went on to say that bromine would have 2 lone pairs, and they have maximum repulsion here of 180 degrees. So the lone pairs very much separated, and then the bonding pairs separated here by just 120 degrees. But there was something that did not sit right with VSEPR. I want you to stop for 1 minute, think about it, prepare your answer, simply focusing this time around on correcting the student's error in this model of BrF3. Also, I would want you, when you correct it, to talk about the molecular geometry and electron domain geometry of BrF3. So now let's take a look at the exemplar answer. And of course, fluorine with its electronegativity of 4.0, much higher than bromine's electronegativity, which is actually 2.96. So here we have some bond polarity. We won't have a polar molecule though, because the pull of electrons in each direction is equal, and with each of these pulls being towards the points of an equilateral triangle, it would not create a net dipole in the molecule. So BrF3 would have some bond polarity and no molecular polarity. Bromine, as the student mentioned, breaks the octet rule because it already has 7 valence electrons and it engages in 3 covalent bonds, giving it 10 electrons, breaking the octet rule. Able to do this, bromine, because it has access to a d orbital system. But what's really important in this faulty model made by the student is the fact that VSEPR is violated. And what we mean by that is that although you have the 2 lone pairs showing 180 degrees and the bond pair showing 120, what about the lone pair to bond pair repulsion, which is supposed to come in second in this hierarchy? But here, the lone pair to bond pair repulsion creates a bond angle of just 90 degrees. And this is why BrF3 does not actually take on this molecular geometry. Instead, it assumes what is labeled as a T-shaped molecular geometry. So let's consider this diagram right here and what the T-shape would look like. And imagine that this bonded pair right here stayed like that, but another bonded pair came here, and the 2 lone pairs stayed in these areas here. Then we would end up with what is called a T-shaped molecule. In terms of molecule geometry, that's not considering these lone pairs. But when we considered the lone pairs, then we would essentially still have trigonal, which is these 3 points, bipyramidal structure. So this is why we say that BrF3 has T-shaped molecule geometry and trigonal bipyramidal electron domain geometry. Here is its Lewis structure, which doesn't have to fit any specific geometry, just you need to include all of the lone pairs, as you can see here, and bonded pairs as well. What we must bear in mind is that this bond angle here in real models is not exactly 90, but a little less than 90. And to get a better look at this, it's useful to check in with PhET simulations right here for all of the details.